Yeah, hello. Sunaina, can you hear me?
Yes, you're audible, sir.
So let me just share my screen and see everything is fine.
Sure, sir. Go ahead.
Uh, So is my screen visible?
Yes, sir. Your screen is visible.
Okay, slides are also changing.
Yes.
Okay, good.
Sir, we'll be waiting 2 more minutes and then we will be starting at 11.
Okay, sure.
Okay, sir. A very good morning, everyone, and welcome to 8th day of the Deep Learning Summer School by IIITDMJ Jabalpur. I am Sunaina Singh, and it's my pleasure to chair this session. I hope you all are enjoying and practicing along with the sessions. We are pleased to welcome Dr. Arijit Mondal for today's session. Dr. Mondal received his BTech in Electrical Engineering and his MS and PhD in Computer Science and Engineering from IIT Kharagpur. He is currently serving as an assistant professor in the Department of Computer Science and Engineering at IIT Patna. His research interests include cyber physical systems, deep learning, and smart grid. We look forward to learning from his expertise today. Thank you, sir, for joining us today. I now request you to kindly take over and begin the session.
Oh, thank you. So let us get started. So today I'll be talking about recurrent neural network. Probably in this course, you have seen some part of the deep learning, the basic deep learning that you have seen, the feed-forward network, probably you have seen, and also I hope you have seen convolutional neural network as well. So, so now we will look at different class of neural network, and this kind of network is a specialized network primarily used for modeling sequence. So, and there are plenty of data in which we need to model those sequence because the consecutive outcome or consecutive output that we observe from certain system, they are actually related. One simple example is like if you look into the natural language, the way the words are connected. So each word will be probably connected with all the previous word and so on and so forth. If you look for time series data, then it may have a kind of a pattern or maybe a certain observation that you are looking that may be related with some previous outcome as well. So when we have some sort of sequence, we try to model the problem with recurrent neural network. So that is one of the important thing. So the thing is, we are trying to model sequence so that we can answer certain kinds of queries. So gradually we will go into that stuff. Now, another advantage also for RNN is the kind of thing that it can support a variable length input. If you see the deep feed forward network, you have the input vector X or that actually has a fixed length. If you look for a convolution neural network, probably it's taking an image of a particular size. Now, sometimes I can have a different, the input which can vary in length, because if we look into the normal natural language sentences, I can have large sentences, I can have small sentences. So I cannot fix that my input will have always, let's say, 100 words. It can be more than that also. So that is one of the important thing or good part about the recurrent neural network. And this kind of network can actually handle long-term dependency. I will elaborate that stuff. And when we have this sequence, somebody has to take care of the ordering of those inputs token so that we can answer certain kinds of thing. So let's look into a few examples. Probably it will be more clear. So let's say I have a sentence something like this. I went to IIT in 2017. Or the same sentence can be said that in 2017, I went to IIT. Now, if I have to answer a query, when did I go to IIT, then it will be 2017. For a human being, it's not very difficult to answer that query. But when I have a neural network, sometimes it will be the last word that will be the answer. Sometimes it will be the second word that will be the answer. So if I need to identify which word is important, so we have to identify which word is important. And also the thing is, the word position can actually vary because the same sentence can be framed in many ways. So if my model actually learns that you have to answer always the last token, then if you provide the input in this manner, then you will get a wrong answer. So that is one of the issue. So we have to model the sequence, we have to understand the dependencies, and when we try to answer, it should not be a fixed token that will get answered, fixed location token that will get answered, but it should find out the most appropriate token. So that is one of the challenging stuff that can be addressed through RNN. If you look into the second example, let's say there is a paragraph which says I grew up in Bengal, and there are many other kinds of statement, and then there is I can speak fluent, and there is a gap dash. I have to fill this one. Now, if you see this part of the sentences of the stuff, then it's not very difficult that probably one can actually guess that the person will be able to speak Bengali fluently. Now, this word is related with a distant past. So I need to track long distance dependencies. So that is another challenging stuff that we have to take care of. If we had some CNN kind of model or the deep feed forward network model, the issue will become it's a fixed length. So that is one of the issue. And then all those things are basically works mostly on the position dependent kind of stuff. So here the sequence is important, the position may not matter. So that we have to take care of. The third example, if you see, the food was good, not bad at all. And so this is one sentence, so we can understand what is actually it's expressing. If you look into the second sentence, the food was bad, not good at all. Now, if you look into these two sentences, they have exactly the same set of words, but these two sentences carry different meaning. So, if we need to build a model, or if you need to have something that can distinguish this kind of stuff, so therefore the model has to understand the sequence. Because if we do not look into the sequence of the different words, then we will not be able to answer the appropriate query. So that is one of the another challenging stuff. So it should be something like position independent kind of thing. It should be long-term dependency that I have to take, and the model should not look into the word only. It should look into the sequence to extract the meaning. And there are many words in English that can mean different kinds of stuff. Like if you have bank, then this bank can mean actually the financial institution, or it can mean a river bank. Now, when we go through some sentences, we can easily understand what kind of bank it is actually referring. So that is also another challenging stuff to model through RNN, or when we try to model the natural language. So we will look into how to model this sequence in great detail. Now, when it comes to modeling of the natural language thing, if you look into the earlier stuff, the pre-deep learning era, then they tried to use some sort of technique, which actually I have listed here. And these are, well, when you have a small chunk of data and you are focusing probably a very restrictive area. But when you try to have a generic chatbot like the chat GPT kind of stuff, so these kinds of method will not work. So there are methods through which you can analyze certain things. I will not go into the details because these are a little bit dated techniques, but it's good to know to some extent. One of the thing is the bag of words. It basically tries to identify which sets of words actually appeared on the document, and based on that it will try to predict the certain kinds of output. Now the example that you have seen here, so if you look into the bag of words, then these two sentences that we have seen have the same set of words, but they carry actually different meaning. So it may not be a very good thing to apply in certain kinds of scenario. And then people have came up with different kinds of measures, which basically tries to identify the presence of certain kinds of words after some kinds of pre-processing. Because if you take a natural language text, then it will have lot of punctuation marks, many other kinds of things. So you have to do some sorts of pre-processing so that you can try to identify the actual meaning. So people have came up with many different kinds of hand feature rule, probably I will say, so that it can probably measure some sorts of similarity between documents. But it works well for certain kinds of scenarios, but may not be very good for a very generic kind of stuff. Then another model is also very important called n-grams, where it tries to look a sequence of words together. So let's say I may want to see two words at a time and then I predict the next word, or maybe I look into three words at a time and I predict the next word, and so on and so forth. But the problem here is that you may have to look for a large sequence, so which is also a very problematic part. So these are some traditional thing for the NLP. I will not go in details. So these kinds of problem can be overcome from your RNN stuff. And when we talk about RNN, we mostly use the natural language processing, though RNN can be applied for many other kinds of stuff as well. but in this lecture we'll give examples mostly from the natural language stuff. Now, when we have to model this natural language, the one of the important thing is that we will have some sort of English word as my input, and I have to predict probably, let's say, the next word or some other thing that I have to predict. Now, I will have some kinds of a model, deep learning based model. Now, one of the important thing to remember that I cannot feed this word as it is. The ASCII text, I cannot provide it to the model, and then it will predict that stuff, because this model will know only the real numbers. It does not know the text character. So effectively, we need some mechanism through which we can actually model the word. And in general, when we talk about the natural language processing, we try to choose the word as the base token, because word actually carries some meaning, and sequence of such words carries the complete sentence, and that provides some kinds of a meaning out of that stuff. So therefore, what we need to do is that we have to model the words in some sort of with real numbers. So this method is actually not valid. Now, in order to model the word, we have primarily two choices. One is that we use one-hot encoding. So in this one-hot encoding, let's say I have word deep. So I put one position for deep, and then I put one only at that position. For rest of the position, it will be zero. Similarly, if I have some other words, maybe one will appear at this position and all the elements will be zero for that case. So it's one hot encoding, only one element will be one. So the issue with this one hot encoding, this vector that you get as an input will be almost equal to the vocabulary size. So in your vocabulary, let's say if you have 50,000 words, then each vector will be 50,000 elements long, so which is not a very efficient one. Then people have came up with some techniques through which they try to model the word with a set of real numbers. It's also a vector, but this vector size is much less than vocabulary size. And the technique that people actually use is called the word embedding. So there are certain methods through which you can model the words in the form of a vector. And the basic intuition for is that if two words have the similar meaning, they should have the same vector. So that is the guiding principle, and there are more into it how you can do that. So if so the basic idea, if two words are actually similar, they carry the same meaning, then probably they will have the same vector. So for our case, what we will assume that we will have a real number as an input. So it's a kind of a vector for some word. It will pass through some model and it will give me some kind of an output. And this real number has to map back to the original word or the word in the vocabulary, so that it makes some sense for the user. Because if I give this as my output, then people will not understand what does it actually mean. So the input word has to be modeled through word embedding in real number, and the output that we get from the model has to be mapped back to the vocabulary so that we can understand what it is giving as output. Now, if you look into this natural language domain, to what kind of the kind of processing that we need to do. So one of the stuff that you have already seen is the feed forward network. Like if you look into the image classification problem, you take one image as an input, you may have some hidden layer, and then you provide some kinds of a classification. So this is my output layer. Now, in case of natural language processing, the problems are pretty interesting. If you look into this image captioning problem, so the problem is you are given an image, you have to generate a caption for that image. So you take just a single input of fixed dimension, and when you are producing output, it will be sequence of words. So I have to produce multiple words for that image. So effectively, this is a kind of a mapping one to many. So I have one input and I have many outputs. If you look the sentiment analysis, it's a kind of a reverse stuff. So in case of sentiment analysis, I have been given a text and I have to classify whether it's a positive sentiment or it's the negative sentiment or maybe on the neutral. So I will have a sequence of words, and finally I would like to say that it's positive or it may be negative. If it's, let's say, if I have to do a binary classification for sentiment analysis. So this is a kind of a scenario. I have many inputs and I have a single output. So it's a many to one relation. Another kinds of problem like a video frame labeling. So what I have to do is for every frame, I have to label what kind of things are present, or maybe let's say I have a video and I have to mark what kinds of activities actually happening over the different frames. So in that case, what will happen? The video is nothing but a collection of images. So I look into all those images. So I have many inputs, and for every image, I try to label what kind of activities somebody is doing. So effectively, this is a many to many kind of relations that we may also come across when we do some sorts of language processing and other kinds of processing as well. And the finally, this language translations is also a many to many kind of stuff. Only thing is that we first look into the whole inputs and then we start predicting certain kinds of stuff. So language translation means, let's say somebody has given me some text in English and I have to translate that language into, let's say, Hindi. So, so in this case, once I look into the whole set of inputs, I'll be able to generate the final outcome. So it's a many to many, but it's kind of a skewed one. Once I see everything, then only I can proceed for the actual translations. So these are the typical applications in the language processing. So I can have many combination. It may not be just simple like one to one that you have probably seen in the earlier lecture. Now we have a more generic kind of scenario, and this kinds of scenario can be addressed through your RNN. Now coming to deep into this RNN. So how we actually model the stuff. So, so let's say I have some sorts of words, W1, W2, W3, and so on and so forth. Okay. Now, a very simple thing that you can assume, let's say I have looked into these words and I want to predict this fourth word. That is our goal, let's say, for the time being. So that means I have seen some part of my syntax and I want to predict the next word. So what I have to do, so if I want to have some kinds of a model, so my model will take this word as input and then it will try to produce the next word. So that is the basic goal. Now, when we have this deep learning based model, what we try to do, along with the input, we try to introduce additional set of weight parameters. So I'm representing it as theta here. So I look into all the words and then I use some additional set of parameters and then I predict the next word. Now the th now the problem will what will happen if I try to predict W5. Now I need another model, let's say F prime, and in this case I'll be taking all these four words as my input, and probably I need probably another set of parameters, let's say theta prime, to predict the next word. because now my input has been changed. So I may need more number of parameters or whatever may be. So I will have a different sets of parameters through which I probably can predict. So now you can easily understand that this is not a very viable scenario. So what we try to do, we look into this set of words and we try to summarize all the previous words into a kind of a state. And then we take this state as input for to predict the next word. In that case, what we will do, we basically look into the state vector. Let's say at time point, if I want to predict the tth word, so I look into some kinds of a state up to t minus 1. I have some additional set of parameters to predict this thing. So now what is actually happening, this s t minus 1, it basically stores a kind of a summary of all the previous token that it has actually seen. So in this example, there is no input for the time being. So if I can have some kind of a summary of all the past observations, then I can have a function something like f, or I can have a single model that takes the past summary of the past observation as input, and then it predicts the next observation, and the parameter theta is actually fixed. Now if I want to predict s of st plus 1, then I can actually, what I can do, I can provide, if in that case I will provide this as my input and my theta parameter will remain the same. So I can actually utilize the same model. So that is the advantage. So over the time step or over the different steps, I'll be able to utilizing this parameter theta. So that is one of the important concept in recurrent neural network. So the takeaway from this one is that we, whatever we see the past observation, we summarize into a state, and from that state we use the weight parameters, and then we predict the next word. And these weight parameters will be utilized, the same set of weight parameters will be utilized over the different time step. So which is one of the uh, important idea, so that I'm not increasing the parameter count. I have a fixed set of parameters, so which is beneficial for computation. So the kind of stuff that I was talking earlier, so now here you can see that we have some sort of summary from the past, and we have the current token, and we use the some set of weight parameters, and then we predict the next word, that is so we are predicting the next word. So that's the kind of idea. So effectively, in a neural network terminology, we call this state is a kind of a hidden state. So that's the hidden stuff. We have the input, and we have the theta, and we have the outcome from the hidden state. So effectively, if you look into this HT that we are actually predicting, that will depends on all the previous inputs in an indirect manner, because HT depends on HT minus 1 and XT. Now HT minus will actually depend on HT minus 2 and your XT minus 1. And if you proceed further, then you will see that it will depend on xt minus 2 and so on and so forth. So effectively, this ht will depend on all the previous inputs. But it's a kind of a lossy summary, but it's a kind of a summary that we are putting in ht. And if we can put good summary in ht, then we will have lot of benefits. So that is the basic idea. So we actually model this stuff with a kind of a very compact representation of this form. So we have some kinds of inputs, we have some sorts of hidden state, and we have some sorts of feedback because ht to uh, ht minus 1 to ht. So that is the kind of feedback that we are actually applying here. So, so this is the compact representation. If we unfold the stuff, we take h, we take xt minus 1, we predict ht minus 1. Then again, we have the inputs, we have the previous stuff, ht minus 1, and then we predict actually ht, so on and so forth. So if we unroll this diagram, we get this sort of diagram. So this is a system with actually inputs. And the thing is, uh, if you have the system with inputs, what you can actually see that effectively your HT will be function of all the kind of stuff. So here, what we try to mention that we are representing in a very compact form, but if we try to unfold the stuff, effectively it will be some function GT that actually depends on all the kinds of token. So that's the basic idea. So unfolding process have actually some kinds of an advantage because it's regardless of the sequence length, your model will have the same input size because this is your input. The input size is actually same and fixed that we have talked about. But if you look into this thing, your input will vary depending on the time step. And we use the same function at every time step. So our neural network model function is also same and the parameter also remain fixed over the time step. So because of that, it can be trained with fewer example and the representation wise is compact. And if you do the unfolding, you will be able to visualize how your information actually propagates across your network. So this is a kind of a example. So when you have recurrent neural network and you have a connections from hidden state within the hidden state. So we have input, we map with some metrics, we have hidden state, and so this hidden state will depend on the past time step and the current input. Based on based on that, H will be determined. We will actually modify this H to produce some kind of a output, and once it predicts some output, we can actually compute the loss based on the golden label that is available with me. So between this Y and O, based on that, we can actually compute the loss value. So this is the kind of structure that we have already seen. Now, if we unfold the stuff, it's not very difficult to visualize that we have some input xt minus 1 that get transformed with u and the previous hidden state that gets transformed with w and that produce h t minus 1. And this ht minus 1 will get mapped by v to produce ot minus 1, and these two will give me the loss at t minus 1th step. Similarly, in the next time step, it will follow exactly the same set of stuff. One important thing to note, when we are doing this computation, we are using the same set of metrics. So this U or W, they will be actually shared over the time step. If we unfold the diagram, it gives me the clear picture how the information is flowing, and all the W's that you can see here, they will be the same. So that means if we unfold, we are not increasing the number of parameters. So that is one of the important stuff. And we can actually proceed in that manner. Sometimes what can actually happen that you may have a feedback from the output. So instead of feedback within the hidden state, you may have a feedback from the output. So in that case also, one thing that probably you have to know that if we unfold the diagram, you can easily see that we have some inputs and that gets mapped with U, and the previous output uh, that will get mapped with W produce HT minus 1. We have V, and that produce actually O, and we can compute the loss. And now when I have the feedback from the output, this HT will take the previous output as an input to compute this HT. Now, and if you unfold, you will get a picture something like that you can see on the right hand side. So one thing to note is that when if you have this scenario, when you will be doing the training, you will predict something wrongly. So OT can be an incorrect prediction. So during the training, what we try to do, we feed the original label as the input for the hidden state. Because during the training, I have to learn the right stuff. So loss will be computed between Y and O. But when I compute the HT or HT plus 1, I will provide the golden label as my input for the HT. But during my testing, I will use this OT minus 1 and OT, because during testing, I will not have I will not have these values available with me. So therefore, we cannot feed YT minus 1 to HT. But when we do the training, we have the label available with us, and we can actually uh, provide that input to the hidden state. This is a kind of an example like the sequence processing for sentiment example. So we look into the kinds of words. Each words we are taking, we are transforming it with some metrics, and then it basically summarize into HT minus 1, then HT, and all sorts of stuff. And finally, based on this H tau, we try to predict some kinds of a thing, and then we compute the actual loss. So this is a kind of a diagram that you will observe when you have like a kind of a sentiment analysis, because you will be computing the loss only once at the end of the step. Earlier examples we used to we have shown that we are computing the loss at every time step, but that may not be needed for certain kinds of applications. You can have a stacked on the deep RNN. So this is a kind of a unfolded diagram. So we have 3 layers of RNN. So here we have some kinds of a feedback. Here also we have some kinds of a feedback. Here also we have some kinds of a feedback. So therefore, when I unfold, this H11 will provide information for H12, and this will provide information for H21. So if you try to see, if you want to compute this value, then you need to have this value as well as you need to have this value. And in order to have this value, you need to have this value available to you. So effectively, if you want to compute this thing, you should evaluate all these 3 things, then only you will be able to evaluate that stuff. So though it's a kind of a feedback that you have, if you unroll the stuff, you will get a directed acyclic graph. So there is no circular loop once you actually unfold the thing. And that is one of the disadvantage of a RNN, because if you want to compute this thing, let's say, then you have to compute all the remaining stuff, and then only you will be able to compute the whole stuff. So there are a lot of dependencies, and because of the dependency, you cannot apply parallelism to a great extent. So that is one of the major drawback of your RNN. So now coming to more formal definitions. So this RNN function that you compute is basically a kind of a Turing machine. So in terms of the expressibility, it's good. It can express many kinds of things. So that's a kind of a theoretical results. And if you see how we actually model the stuff, so the kind of mathematical expression that we use is as follows. So we have this input xt, we have the previous state ht minus 1, with the input get transformed through u and hidden state get transformed through w, and we have some sorts of bias b that calculates the pre-activation value at. And in this hidden nodes, the activation function that we use is the tan h. So I hope you know the tan h function, which basically lies between -1 to +1. It's almost like a sigmoid function, but it lies between -1 to +1. And once you compute the hidden value, you can actually compute the final outcome yt. So which will get transformed through some V matrix. You may have some kinds of a bias for that. And probably if you want to predict some kinds of a label, or if you want to classify, and on yt, you can actually apply the softmax. So in this case, you have the input and output have the same length. So that's the basic RNN that we use. So in case of like the sentiment analysis, we may not look into the individual output at every time step. We look into the last prediction only. So the thing is, a few things. This expression computation of this thing is exactly same as deep feed-forward network, which is the linear combination. Only thing, it takes a feedback from itself, and then we actually apply a nonlinear transformation through the tan h function. And this is the typical output step that you have already seen for any kinds of classification. Now, here's a nice example. So what this guy has done, instead of predicting the next word, he tries to predict the next character. So how RNN actually works, that will be more clear. So it feeds some kinds of a character as an input. And let's say for the time being, we have only 4 characters in my vocabulary. And we actually model as a one-hot encoding. So now, so we give H as an input. So that means we have to model as a one-hot encoding. So H is specified in this manner. So the first element will be 1. And then it has some kinds of a hidden state, hidden layer. So based on the input, and you have some kinds of a matrix WXH. So this basically shows the input to the hidden state mapping, and based on that you get some hidden state value. And this hidden state will also get mapped through hidden state to output, and you produce this output. Now here we have to predict a kind of a single character, so we have to take the softmax of these values. But here we are showing the final values after the linear combination, before, without taking the softmax. Now here you can see that if the word that I'm trying to predict, or the character that I'm trying to predict, is hello, so the next character should be E. But if you look into these values, then you can see that 4.1 is the largest value. Effectively, it will be a wrong prediction. So it was supposed to predict E. That means it was supposed to predict this value. That value should be the largest, but it's predicting some kinds of a wrong stuff. So that is the first time step. In the second time step, it takes the input E, which is again encoded with the one-hot encoding style. So this value is 1, and based on the previous state and the input and all those metrics computation, it updates the hidden state as follows, and from the hidden state it tries to predict the next word. And again, you can see that it was supposed to predict hello, but it's predicting incorrectly because this is the largest one. If you look into the third time step, it's the input is L. So third position will be your 1 because it's one hot encoding. And after the matrix transformation from the hidden state and the input, you get something, and then you are trying to predict the next word, sorry, next character. So here you are supposed to predict L, and if you look into these four values, then you can see that 1.9 is the largest. So now it is actually predicting correctly, and it will continue to do so. So this is the way it actually works. The one important thing again I want to stress, like when we are transforming this input here, we are using these metrics. So this matrix is actually shared over the time step. Similarly, this matrix will also be used over the time step. At each time step, the same matrix will be used. So this network can be represented in a compact manner in this way. The right hand image that you can see. We have xt, we have some weight parameters between input to the hidden state. We have some weight parameter from hidden state to hidden state. We have another weight parameters from hidden state to the output state. So that's the basic idea of RNN. And what this guy has done, he actually trained this model, this simple network, with certain kinds of text. So I would recommend you that you should go through this reference when you are free and read it more carefully. You can understand the powerful nature of RNN. So what he has done, so he has given this the text from William Shakespeare, and so it has learned the text of the William Shakespeare. Since it has learned the structure of those characters, and then you can use it for some kinds of a prediction of the next character. Now if you look into this stuff, this is actually the outcome from this generator, from this RNN. If you see this one, so alas, I think he shall be come approached and the day kind of stuff. So you can understand that it's not at all a correct English, but the kind of structure that it has generated is looks like how the William Shakespeare used to write. So when it looks into the character, the model has actually learned the structure of those characters. It has learned some of the words, but probably it has not learned the meaning. So that's why it's generate a structure which is similar to the William Shakespeare writing style. So this is this one. This is another example. Many of you have probably seen the LaTeX to write the mathematical stuff. Now it has generated some kinds of a mathematical proof, but this proof is also not correct. If you go through some of the sentence, you will find that it's absolutely absurd thing. Only thing, it has learned how the structure looks like, so it has generated some set of characters which similar to the given inputs or the training samples. So this is also in some kinds of a mathematical stuff, and this is an example. So here, this character RNN was trained with Linux kernel source code. So in this, so this is a C source code, and then once it actually learns this C source code, or it was trained with that one, it has learned the actual structure, how the program is actually written. So you can see that it has generated nice stuff, kind of a the header file that has to be included, and the kind of steps that one has to run. So if you look into this, stuff, then you will understand it looks like a nice C code, but this is actually doing some kind of a garbage stuff. So one easy thing that you can understand, it is initializing with some garbage string. It has no meaning. So this character RNN has actually learned the structure of the text, structure of the characters that are present in the input. but it has not learned the meaning. But it ha- but so this actually shows that it can learn a very interesting thing, provided if we feed the more meaningful stuff. So the good part of RNN is that it can process any length of input, and we can have we can actually remember the distant past also, because it summarizes all the previous input token. And one of the important stuff that I have already mentioned, that the input model size does not increase for a longer input, because it uses the same set of weight parameters at every time step. So the weight parameters are actually shared, so which is one of the major benefit for the RNN. The problematic part for RNN is this: the computation is slow, because I have already told, if you unfold the stuff, it's a pure directed acyclic graph and there are more complex dependencies. So therefore, the thing is, you have to do some sorts of sequential computation. You will not be able to do much of parallelization, so which is one of the major bottleneck. And since the path can be too deep, effectively, uh, the information that gets propagated across the network will be very small. So, which is one of the bottleneck, and that is known as the vanishing gradients problem. We will come to that part. So, if so, there are certain issues with RNN, because if it is a distant past, we may not be able to carry forward the certain stuff. So that can be a challenging as well. So now, one of the important thing that now we need to look that how we actually learn these weight parameters. So that is important thing. We have seen this diagram. So earlier we have some kinds of inputs. We map it to hidden state. So the hidden state will be mapped from the previous hidden state and from the input. And based on that, we will be computing the output, and we can compute the loss based on the Y2 and O2. So every time step we'll have some output, and we can actually compute the loss. So the computation of loss will be at every time step. So that's the kind of a generic scenario that we are talking about. In case of sentiment analysis, we may not compute this L1, L2, L3. We only compute the last loss, because it's just a single thing. So here we have an assumption that we try to predict, let's say, the next word or the next character. So the moment I make a mistake in prediction, I compute that loss, and the loss will get accumulated over the time step. And all the losses will be accumulated over the time step, and we will compute this loss. Once we have the complete loss available with us, then we can go ahead for the back propagation. Now, one of the important thing is that if you look this W weight parameters, then these weight parameters actually affects the loss through many paths. So it affects the loss through many paths. And we have to, in order to compute, say, del L by del W, we have to accommodate all such paths in our computation. So that is one of the most challenging thing here. So we'll be talking about that stuff, how we can actually compute the thing. But just before going into that stuff, so if you want to compute the gradient, so network needs to be unfolded, and then we can actually do the backpropagation of the gradients. I hope you are aware of the backpropagation method. And one of the thing is that you have to decide how much unroll you want to do. So because we have to unfold the system, and then we can do the backpropagation. So we have to decide how many steps we want to do this unfolding. So that has to be decided. So there are two issues that people actually come across in such kind of a model, which is the vanishing gradient and the exploding gradients. We will come back to that part a little later. Now, the loss function that if I need to compute, then we have some input which is nothing but the mean square error. So that is the loss in a single time step. And if you want to compute the loss for the over whole time step, then you have to sum up the whole thing. So this is the loss at single time step. So t is a parameter here, and we are summing over t up to tau time step. So that will be the loss if you are considering the mean square error. You can also consider, depending on your problem, you may have to consider the cross entropy loss, which is nothing but exactly it will be similar. So every time step, you will have some sorts of predictions, and you have to sum over all the components of a time step and then sum over all the time points. And and the kind of method that we actually apply called backpropagation through time. And since we actually truncate with tau time step, we sometimes this is also called the truncated backpropagation through time. So in case of RNN, we cannot apply backpropagation directly. We have to apply backpropagations through time. But the idea that we will be extending almost similar as the backpropagation. But we have to take care of few things. So before jumping into the actual stuff, let's look into this scenario so that we can understand the backpropagation through time. So as of now, what we have actually talked about, this ht that we are computing is a function of xt input, the previous time step, and a kind of a weight parameters. So here, if you see the previous diagram, so we have one mapping from xt to ht with u and another weight matrix from w to h itself. So here, this WH basically combines both the stuff for the time being. So we are not distinguishing the weight parameters from input to the hidden state and hidden state to hidden state. We are representing just a single weight parameters for the time being. And the output that we will have will be kind of the HT that will get mapped. We will have additional set of weight parameters, and probably it will get mapped through another function, let's say G. Now, the thing is, so this dynamics is almost similar to our RNN. So if we want to compute the loss over, let's say, tau time step, then we look into tau inputs, we predict tau outputs, we have these weight parameters, and then we actually compute the total loss over the time step. So here OT is a vector, YT is a vector. So we are not showing that additional summations here. So we have to compute some kinds of a loss between YT and OT. We will sum over and we will take the average of those loss. So that's the loss function, total loss that we are actually computing. Now we have to compute this del L, del WH. So how this loss is depends on WH. So we know that we have to apply the chain rule. So what we can do, we can replace L with this expression because this is the actual loss function. So it will depend on the loss over the different time step. So if we try to compute that stuff, so if we want to compute this derivative, then OT, so OT will depend, see this loss will depend on OT because how close I am to the actual value. So this loss will get will have derivative with respect to the OT, and this OT will depend on, OT is nothing but your G function. So this OT will depend on your HT because this is a direct relation. So I have to compute this derivative and then this HT will depend on WH. That is the stuff. So we have to compute this thing. Now, if you look into these first two terms, we can actually compute this derivative because we know the loss function, then we can actually compute this value. Similarly, G function is known to us, so effectively we'll be able to compute this one. The problem comes here because we have to compute HT with respect to WH. So though it appears that this HT depends on WH, but WH also influence HT minus 1. That is one of the issue. Because if you see this WH, then it contributes to HT minus 1 as well as your HT. So there are multiple paths through which it can contribute. So effectively, we have to take care of that stuff. So therefore, if we want to compute del HT by del WH, then we have to take the derivative with respect to WH once and with respect to HT minus 1 once more. So, so therefore, this derivative will be computed once with respect to WH and once with respect to HT minus 1. So here you can, so now we take the derivative with respect to HT minus 1 and then HT minus 1 with respect to WH by applying the chain rule. So now the expression looks a little bit scary and becomes more complicated. So now we will simplify this thing. So we will say, let's say this is my AT, just to simplify the representation. Let's say this is my BT, and let's say this is my CT. The last one expression I can actually represent as AT minus 1 because it's exactly the same stuff. Only thing, the time step has changed for H. WH also remains the same. So I can say it's AT minus 1. So effectively, I can actually represent the expression in a more compact form is something like AT equal to BT plus CT plus AT minus 1. And you can also show that A0 will be 0. So it's a kind of a recursive functions that we are writing. Now, if you unfold these equations multiple times, you can, so if you replace AT minus 1 with another kinds of stuff, AT minus 2 and so on and so forth, you will observe that there will be CT, then there will be a multiplication of CT minus 1 and so on and so forth. So if you unfold the stuff, and if you try to write that expression, you will get a expression something similar to this. You will have a summation of terms, and on each of the term, you will have a kind of a product of CJs, because if you unfold this AT, if you unfold this AT minus 1, then you will get CT and CT minus 1 as a product. So, so you will be able to you'll be able to compute this expression as follows. So this expression looks a kind of a concise form. Now we can actually replace this AT, BT and all those stuff with the value that we have already substituted. So now we can make a very complex expression and which is looks scary, but it's not very scary because we know how to get to this expression. So now the thing is we have actually we know how to compute del HT del WH. So this expression will be used further. This is an example. I will quickly browse through. This is not with respect to RNN. This is mathematical results. So if you see the neural network model, then you have the inputs and you have this kind of a weight parameters based on which you compute the next level of stuff. So effectively, you can say H is a function of X, and we can represent in the concise form this manner. So H is a product of W matrix and X, and the W matrix, if we represent in this manner, then we have to take the transpose. Similarly, when we do the back propagation, we have the gradients available at this node, and we have to propagate the gradient in this level. Then we can also get a nice compact representation that the gradient at this level G1 will be product of the weight matrix and the gradient in this second level. So the thing that I wanted to stress here, this W matrix, either we need to use in the transpose form or in the normal form in order to get certain kinds of output. So if you represent the W matrix in a different form, then we can have also H equal to WX. In that case, G will have the transpose. So, so, so that's the important stuff. So when you compute in the forward path, when you compute in the backward path, it's almost same. Only thing, the matrix has to get transposed. So now coming to the actual stuff. So back propagation through time. So we have seen our uh, expression something like as follows, because we multiply x with u and h with w. So our and o will be available through a transformation of b. So this is the basic network that we have already seen. So the loss we can actually compute again in the similar manner. Now the goal is to compute these values, because we have to compute del L by del W. That is the trickiest part. Del L del U will be relatively easy. Del L del V will be relatively easy, because W actually has internal dependencies. So that we have to take care of. So now if we want to compute the loss, then we have to first compute del L del O T, because how the loss is varying with respect to O that we have to compute. Now we can once we have these values, we can actually compute del L del V, because now it will be a kind of a chain rule. So I have to look for how L varies with respect to O and how O varies with respect to V. So this is a product symbol. I have not written the product. I wanted to stress that these two are the components that has to that has to be multiplied with the appropriate size, because we are writing in the matrix notation, so your dimension should actually match. So effectively, if you do a little bit of mathematics, you will observe that it will be a del L del OT, and this part will actually gives you H transpose at that time step. So we can compute del L del V. Now we have to compute, if we want to compute for the loss with respect to the final time step. So for the final time step, del L del HT can be computed again on the similar manner. So it will depend on how L depends on O and how O depends on HT. And that we can actually compute some sorts of V transpose del L del OT. Now for this, because this O will also depends on the previous kind of stuff. So effectively, the more challenging part is to compute del L del HT. So now we have two components. So how L varies with respect to HT plus 1 and HT plus 1 with respect to HT, and the other component how L actually varies with respect to O and O varies with respect to H. So these two components you have to actually compute, and if you compute that stuff, you will get W transpose and del L this thing, and there will be this expression. Now the important stuff is like we have a situation that we have to compute these value. So now we can see that there will be some sorts of recursive steps. And these steps is almost similar to our AT times CT times AT minus 1, and this is my BT. So we can actually apply a similar kind of trick, and if you try to combine the stuff, then you will get an expression something of this form. So earlier we have seen that it was CT, then CT minus 1, and so on and so forth. We had a product term. Now CT is actually a constant, does not varies over the time step. So effectively, we will get a product term something like this. And this is a product of repeated product. Now, when I have a matrix, this matrix can be thought of, if you do kind of a eigenvalue decomposition, this matrix can be represented through a set of eigenvalues. Now, this actually boils down to, when you take the product, it's actually boils down to the value something like lambda to the power n, if you are doing n times the product for the n times. Now, lambda, the eigenvalue, is a scalar value. If you have this kind of a product, so when you take this product, this eigenvalue also get multiplied every time. Now, if your lambda is greater than 1, then what will happen, that this value will be too large actually. And if lambda is less than 1, then your value will be too small, because if you take the product of less than 1 multiple times, the value will keep on decreasing. So effectively, that will lead to 0. And if the lambda is greater than 1, then your gradient value will be very large. It will keep on accumulated. So this lambda greater than 1 actually goes into the exploding gradient. Lambda less than 1 will go into the vanishing gradient. If it is exploding gradient, the steps that we can take is very easy. We can clip the gradient so that we do not propagate a very large value. But when the gradient is 0 or close to 0, we will not have much scope. So we need to have some other kinds of trick to overcome these vanishing gradients. So now the other stuff can actually be computed very easily. So del L del U, if you want to compute, then how L actually depends on HT, and HT, how HT depends on U. So you can actually compute that stuff easily. So HT-U relations will be determined by this matrix, and del L del HT, we have already shown that how it depends. So we have to reuse that computation. Similarly, with respect to del L del W, it will be also somewhat similar. Now, this HT and W, that will be related with the previous time step, and del L del HT will be computed again in the same manner. So this computation is tricky, and that will be reused for the other computation as well. So that's a kind of little bit more mathematics heavy slides. You can think of later, and if you do it nicely, you will understand easily. It's not a very complex thing. Only thing, since it's being represented with a vector notation, it looks a little bit scary, but it's not that scary. It's simple thing. The the stuff that I was talking, like when you have the vanishing gradients or the exploding gradients, the path that we have, it will become a very large path through which the gradient actually flows. And because of that product, every time you do a product of W, and that can leads to vanishing gradients or can go to and the exploding gradients, because this W will be characterized by the eigenvalues lambda. So that's the kind of issue that we usually face. So these kinds of neural network or recurrent neural network usually called the vanilla RNN. So it's very hard to retain information from a distant past, because the successive matrix multiplication can lead to a problem. So effectively, what people have observed that the hidden states are good to store the short-term information, but if you need to store long-term information, then this vanilla RNN does not perform well. So in order to overcome the stuff, what people have proposed is called the LSTM or the GRU, long short-term memory and the GRU. So the idea is that they use some sort of gating mechanism in order to control the flow of the information. So we'll elaborate that stuff. So the RNN structure that we have seen, we have the past hidden state, we have the input, and we predict some kinds of a hidden state for the next level. GRU, the gated recurrent unit, has the similar kind of structure, but internally it will have some more things. LSTM will have some more stuff internally, as well as it has some kinds of a memory cell, so which propagates over the time step. So we will elaborate these two structure, GRU and the LSTM. LSTM actually means long short-term memory. We will be elaborating soon. Now, so if you look into the history of these two things, people have first proposed LSTM. It's a pretty heavy one because of its heavy nature. The computation was it's basically computation intensive. So in order to overcome that stuff, people have uh, simplified LSTM structure, and they achieve a kind of a gated recurrent unit called the GRU. So in the literature, you will observe that LSTM was first proposed, then the GRU came. But for today's lecture, what we will do, we will first look into the GRU. We will learn the gating mechanism first, then we will go into the LSTM because it's more complex and a little bit more involved. So gated recurrent unit, so it's a kind of an improved version of the vanilla RNN. It's use some sort of gating notions for the propagations of information, so that we will see. It's similar to LSTM because it was derived from LSTM, but it has less number of parameters. So how does the gated recurrent architecture looks like? So it has some sorts of internal gates. So let's look into this diagram. That will be better, and we'll come back to that stuff. So we have some kinds of inputs xt, and we have some hidden state ht, previous one. So how this analogy that we can think of? So xt can be the kind of weather that we have, and ht is the kind of weather, the kinds of clothes that you put on yesterday. And what I'm trying to do is we try to predict that what clothes I'm going to wear for today. And this HT, this tilde HT, probably a kind of a candidate clothes that I can actually wear for the current day. So that's the kind of analogy that we'll be using. So we have this information, the weather today, and we have the clothes that we wear yesterday. We have two gates called reset gate and the update gate. So reset gate will try to reset some information, update gate will try to update certain kinds of information. So this reset gate, what it does is it first computes this RT based on the hidden state and the XT, and then it does a kind of a element wise multiplications. So that means, so this RT actually acts as a gating control. So RT is used, so RT actually computes this functionality. So it's a sigma. So sigma means the sigmoid function. So effectively the outcome will lie between 0 and 1. So effectively I can think of that HT which is getting propagated here, so which is getting controlled by this RT. So if RT is close to 1, whole information will propagate. If RT is 0, no information will propagate. So that is the kind of gating mechanism that we have. So we have some kinds of a reset, and if we do the reset, then we will give more weightage to the candidate clothes for today. And if if it's the other kinds of scenario, then we will not give any weightage to the current stuff. So we will try to utilize the previous thing. So this is, so either I can reset or I can propagate that information. So that is the idea for the reset. Similarly, for the update gate, how much information I want to propagate to the next level. So ZT also, if you see, it's also a sigmoid function. And when you do this element-wise multiplication, you are doing a kind of a getting how much information you are propagating on that front. And then what you do is that you pass some information from this candidate stuff. So you are giving some kinds of a weightage for the past and some kinds of a weightage for the candidate one, and eventually you get the final outcome. So that's the kind of thing. So through this gating mechanism, kind of a weightage that I am deciding, I would like to control the information flow. And one of the important thing to note, earlier when we had the vanilla RNN, we used to have the direct propagation of the hidden state. So in that case, the gradient used to be, the gradient can become 0 because of the repeated multiplication. And in this case, we have this additional plus term because this path can contribute some information. So that actually prevents the vanishing gradients. So that's the idea for your gated recurrent neural network. So this reset gate is basically tries to have the short-term dependency. Update can actually have the long-term dependency, because whatever you have summarized, you can propagate that stuff, and reset will reset the past information, and it will take the current information and it will propagate into the network. So, this now we will come to the long LSTM, long term versus short term. So vanilla RNN carry forwards the hidden state across the time layers that we have already seen. So in case of LSTM, we will have one hidden state and we will have some kinds of a memory state or the cell state. This hidden state will act like a short-term memory, and the cell state will act as a kind of a long-term memory. And again, we'll be using some sorts of gates that we have seen for the GRU uh, uh, to control the propagation of that information. And there is some kinds of a mechanism that some information can be leaked between short term and the goal term. So that actually also helps to control the propagation of those information. So now let's look into the architecture of LSTM. So again, we have these inputs, the hidden state, that's the thing, and the input. And here we use few gates, the forget gate, input gate, and the output gate. And we'll have one more gate, specialized gate called the candidate gate. Sometimes people refer with some other terminologies as well. So now for every gate, the input will be for each of the gate, the input will be your hidden state and the xt, the input that you are taking. You will have this memory which will get propagated from the previous stuff, and this forget gate will try to control the flow of the past information. So this forget gate if you see the when you will see the expression, this forget get basically use the sigmoid function. So it again actually controls the propagation of the information. So either it can forget, it can propagate the whole information, or it can propagate some portion of the previous stuff. So forget get actually helps to forget the memory or not to forget the memory. Similarly, the input gets also tries to do how much candidate information that should get propagated for the next level. So again, this input will use the sigmoid function. This is computed with the tanh function. So this is the normal vanilla RNN kinds of operation that you can think of. So this candidate CT is actually computed with tanh. The rest of the stuff will be kind of a your sigmoid function. This input will propagate some of the stuff, and this also actually combines with the memory cell, because some information can actually also get leaks into the memory. So that is also possible. So, and then you update this CT. So what is happening? Forget get actually controlling the propagation of the flow, and from the input get or the candidate memory, you are propagating some information to the memory the memory cell. And what you also do that from the candidate memory, it also can propagate to the next level. Now this phi actually represents the tanh function. Uh, uh, so this actually gets propagated again through. So this is the output get. It uses the sigmoid function. So whatever you have computed, and that gets actually propagated to here. So that means, so from the memory, some information can get propagated to the hidden state as well. So there will be a path communications between hidden state to the memory cell, memory cells to the hidden state. So this is a more complex structure compared to your RNN. Sorry, more complex structure from your compared to your GRU. Now, if you look into this expression, so forget get, input get, and the output get, they use the sigmoid function because they controls the propagation of the information. Candidate memory that use the tanh function represented with phi here. So that determines the candidate memory, and the memory cell that is actually updated with these two stuff, the addition of these two things. So something comes from the forget stuff, something comes from your input and the candidate get, and the final output will be determined based on the output get and your phi stuff. So that's the functionality of your LSTM. If you see the literature, there you will find this LSTM is actually being drawn in many different avatars. So all basically represents the same stuff. They try to visualize in different manner. So now we will see few applications of RNN uh, for language processing mostly. So if you see the sentence, let's say I have to predict or I have to fill the blank. So I am dash. So in this dash, we can put happy. Probably I am happy. That's a fine thing. And if you see the second sentence, I am dash hungry. Now, when I have this information, then definitely I cannot put happy here. So probably I can put not or very. I am not hungry, or maybe I am very hungry. So when I try to predict a word, I may have to look from the past as well as from the after that stuff, because this word can be governed by the previous stuff as well as from the next one as well. if you see the third sentence, let's say I am dash hungry and I can eat a full tandoori. Now the thing is, if I say I am not hungry and I can eat a full tandoori, then it makes no sense. The sentence meanings are not very clear. So now the thing is, if I try to really predict this word, then I need to have some mechanism. I look into the past set of words, I look into the future words, and then probably I will be able to predict the current word. Because if I just looked into only this word, and if I'm trying to predict this word, then I may not be able to predict correctly. So how to handle such scenario? So what is being done here is that we use a bidirectional RNN. So what it does is that it takes the input. If you look into the blue path, then it's the normal RNN that we compute. So it takes the kind of an input and keeps on looking into all the inputs. So, and there will be a kind of a masking for the this input, because we will not be able to, we do not have that input. So this is a diagram that has been unfolded over the time. So we look into the token X, and we compute the stuff as well. We keep on propagating that information. Now, once we reach to the end of the stuff, we start this computation, the red path. So this H forward is one RNN, H backward is also another RNN. Now, this H backward will look this word first, then this word, and so on and so forth. Now, so we will call this is a bidirectional RNN. So this blue and the red, that these two things together represents one RNN block. And once we compute these two values, and these two values will be concatenated to your O1. So O1 will be computed only when you have looked into the forward path and you have also come back from the backward path. Then you can actually compute O1. And then you can compute the loss based on the Y1 and the O1, and so on and so forth. Now, if you have this structure, then if you want to predict this word, you will be able to predict more meaningfully, because you have looked into the past sequence, you have looked into the post sequence, and then if you want to predict the third word, your prediction will be more accurate in that case. So that's the applications of bidirectional RNN. There is another applications of RNN called the machine translations. So in case of machine translations, what we have seen earlier, or what we have talked, so it's many to many. So inputs and outputs can have varying length, and we will use encoder decoder kinds of model. So we will have a kind of scenario that we have the inputs, and we take the all inputs and we combine into a context vector, and from the context vector we start predicting we translate in another language. So the idea is as follows. So we look into the input, we go through all the inputs. So here we are trying to translate from English to Kannada, and the sentence is I know Kannada. So we have some start symbol and we have some symbol just to mention that it is the end of sentence. And then we summarize the whole step into a context vector C, and that context vector is propagated to the next level of the decoder. Decoder is also an RNN. Now, this, when we are saying this is an RNN or this is an RNN, it can be an LSTM block, it can be a GRU block, or it can be a vanilla RNN block. So most of the time, maybe you will be using the LSTM block or the GRU block. But this is the, in terms of theory, this is nothing but it's a kind of a RNN network. So the thing is, we compute the, so this is my inputs. The internal state that we get will get summarized over all the past inputs. And then we actually compute the context vector based on all the hidden state that we have seen so far. Now, when we try to compute the output state, uh, what we do, we have this context vector and we look into the past outcome. And based on that, we try, sorry, this y t prime 1 is the past outcome. And what was the internal state in the previous step? Based on that, we are trying to predict your st prime on the in the current state. So suppose I want to predict for this word, then I have to look what I have predicted this one, because this is this is the stuff that I have to feed back, because I have predicted certain words. Based on that, I have to predict this one. So S2 takes input from the previous hidden state. S2 takes inputs what have been predicted in the previous time step. S2 will also take this context vector as an input. So C is not shown explicitly here for S2 because this is an RNN. So effectively there will be a feedback and then there will be a context vector that is actually coming in. So C will remain fixed for each of the time step for the decoder part. So this left hand side will be called the encoder part. And once we do this encoding, we create the context vector. Using the context vector, we start decoding the stuff. So this is an example for your encoding decoding mechanism. So, so one of the issue with this one, like when we are trying to predict these words, we have a constant context vector. So which is not a very good thing, because we just summarize by looking into the whole input, we summarize the whole thing into a single context vector. That may not be a very good thing. So what we need to do is we need to change the context over the time step. So what we have said that this context vector will be input for all the time step, and this is actually a fixed. So what we do not want is that we do not want this context vector to be fixed for each of the time step. We want different kinds of a context because we are predicting a new word. So every time I would like to change that context. So what people have come up with called the attention mechanism. So in the attention mechanism, what it does is, if you look into this diagram, then this below portion you can see it's exactly the bidirectional RNN, because we have some forward path and we have some backward path. So this is the kind of stuff. Now, what we do, we try to combine the outputs of each of the time step here, each of the time step here. And one thing here is that we try to give some kind of a weightage to alpha, which is represented as alpha T1. Now we earlier we have talked about that. Let's say this gives me outcome O1 and this is O2. Now, what we do, we try to give some kinds of a weightage to O1 through this parameter alpha T1. Similarly, O2 will have weightage alpha T2 and so on and so forth. So through this, we try to compute the context vector. Earlier, we used to have a single context vector. Now, the thing is, we would, so this alpha weight parameter will be coming from another neural network. So what we do, so this is another neural network. So what we do, we take the hidden state as input. HT means the combined stuff, both forward and the backward. So the red line basically nothing but the O1 from the previous diagram. So it takes the complete hidden state as input, and it takes the previous state from the decoder stuff, that as an input. So it basically knows what is the current state of the decoding part, and it looks into all the input words. Based on that, it computes the weightage, and this alpha Q1 will be used here. So that means when I am predicting certain words, I can keep on changing this weightage. So for certain position, I want to give more weightage to this word. For certain position, I may want to give more weightage to this word. So I can have a scenario when I can give the weightage in a varying manner. Effectively, that means my context vector will keep on changing. I will not have a fixed context vector. And if I have a good neural network model, then I will be able to provide attention sometimes to the first word, sometimes to the second words. So that means I can give attention to the appropriate words. So that is the basic intuition for the attention. So once you compute this and then in order to compute the output, you will take the decoder hidden state as input, you will take the context vector, you will produce this YT. And again, when you want to compute the next one, you will have another context vector CT plus 1. It will be computed with all of those, but you will have a different weight parameters at that time. So we want to give weightage or we want to give attention to different words at different points of time. So, uh, so one of the thing that I would like to mention. So this model is pretty complex that you can understand, and it has lot of dependencies. So therefore, the problem is it's very difficult to parallelize. And the important thing nowadays, people do not use the attention mechanism with RNN. There is nice structure called transformer model. Probably you will see those lecture on later part of this course. And through transformer, you can actually you can mimic the attention behavior. And the important stuff is that it does not have more complex dependencies. So you can actually parallelize that stuff. So all those chat GPT and the transformer network that actually uses the attention, but with a different kinds of architecture. So now I will show you some examples for NLP kind of stuff that has both image and visual content. So if you look into the image captioning problem, so given an image, we have to predict the caption. So what we usually do is that we look into the image, and that is passed through a CNN, and then we do some kinds of flattening of the properties, and that properties we actually feed to the RNN. So that means we extract the feature from the image, then we create a context vector that you can think of, and that context vector is passed into the RNN, and based on that, RNN will start producing the kind of token, the kind of words that it has already learned. So if you have a scenario when you have to model both image and text. For text, you will be using RNN like structure. For image, in order to extract the feature, you may have to use CNN kinds of structure. So this is this image captioning problem. So these are just an example where probably you are able to produce some good captions. Sometimes the system can actually fail miserably as well. So, i- so, so if you see this image, then it produces like a person holding a computer mouse on a desk. So, which is not a meaningful stuff. So, because it's a statistical model, it may not be able to predict correctly, but many times it can actually predict correctly. Another kinds of problem, just to elaborate, like visual question answering. So you are given an image, uh, you are given an kind of an image, and uh, you are given a question also. So and you have to answer that stuff. So if you see, so you are given an image, and what is the sports position of the main in the orange shirt. So so you are given one visual information, one text information, and you are supposed to produce some kinds of an output. So this is a very challenging problem because you have to understand the image, you have to understand the text. Based on that, you can actually um, mm, you can produce your answers. So in order to do that, what you have to do is probably you need one channel for your CNN stuff that actually summarizes the feature content of the images, and we then create a kind of a flattened embedding of the image. So the way we can think of, we have an image, we pass it through some CNN architecture, let's say VGGNet or something, and then we create a flat embedding of 1024. That means this 1024 embedding is a kind of a representative over of this image. Similarly, the kind of text that we have input, we also pass it through LSTM, and finally we create some sort of an embedding of the inputs. So the thing is, we can think of it's a kind of a context that we are creating, one from the image side and one from the text side. And then we can do a pointwise multiplications, and then we can have some sorts of fully connected layer, and then we produce some sorts of output. The point here is that I wanted to stress is, if you have a mixed up image and text, probably you have to have two channels. One channel will process the visual information, another channel will process your text information, and then probably you have to fuse these two things together, and then you have to get the answer. Like in case of image captioning, you first process the image, and then you give the context, and then it will generate the caption. In case of visual question answering, you have to fuse these two things together. So probably you need two channels, one dedicated for image and another for text. And then you fuse these two things together and get your output from that thing. And then there are plenty of applications. I have not listed others. So these are the primary stuff. That's why I just mentioned. So as a summary, so RNN is actually good to model sequence, and it can actually capture the sequence behavior. LSTM GRU can actually handle large sequence. That's the good part. But the problem is with this thing, you may not be able to do a lot of parallelizations. So that is one of the bottleneck, because of which the transformer is the more important model that people use to do. And the good part of RNN that we have talked about, that it can handle variable length input. And when you want to update the weight parameters, you have to apply the back propagations through time. So that is one of the important thing for you. So with this, I will stop, and I have another 10 minutes kinds of left. So I would like to take questions, because for last 2 hours I have spoken. Now I would like to see if there is any questions.
Excuse me, sir. There are certain questions in the chat also. So please have a look
Okay,
at them.
okay, just a second. Uh, Somebody has asked how to get these weight parameters. I think I have already mentioned how to get these weight parameters. So the weight parameters has to be learned, and that is learned through the backpropagation through time. The second question, what is meant by sentiment analysis? Sentiment analysis means you are given a text, you have to say whether the sentiment is positive or sentiment is negative. So, like, I like this movie. So it's a kind of a positive sentiment. I did not like the movie. So it's a kind of a negative sentiment. So that kinds of analysis, like if you have some kinds of a review, like say Amazon review or certain kinds of stuff, so the backend AI probably tries to analyze whether it's a positive review or it's a negative review. Based on that, it tries to compute certain things. So weight matrix shared over the time step means it is shared within one fold or between various epochs in the training process. So uh, see, the over the epochs, the weight parameter will get changed, because in every epoch the weight parameters will be changed. The weight parameters are shared over the time step. So when we compute this thing, we unfold the RNN, let's say 5 time step. Now in this 5 time step, I have the same weight parameters. So therefore, we use the same set of weight parameters only in this 5 time step. And this 5 time step consists of just a single epoch. The moment I go for the next epoch, my weight parameters will also get against change. In the next epoch, again, there will be 5 time steps. So in those 5 time steps, the weight parameter will be shared. That's the idea. For what other applications other than NLP we can use RNN? So if you have any kinds of pattern recognitions, like if you go for time series modeling, the pattern modeling, sometimes we can also use RNN as well. Because when the sequence is important, we may have to do that stuff. So, like if you want to do kind of a video processing, then it has the sequence in Notion, because it's a collection of images. The images will have certain relations. So I want to extract that sequence information. So I can actually use this RNN. So how can we unfold and visualize the loss computation and state and answer states and input and weight matrices, etc., and how to interpret that using the code? It's a very complex question, not very clear. So one of the thing that I would like to suggest, you look into the example that I have shown, character RNN. You browse through that blog, and that blog actually will provide lot of answer to your query in great detail. So when we have these inputs, we try to predict certain things. There also we can actually visualize in which word or in which character I'm trying to stress. So there are certain kinds of visualization for that. And you if you develop a RNN code from the scratch, you'll be able to understand this loss computation more clearly. But typically, we use the library, so the loss computations will be more or less hidden from us, the actual computation. Only thing we have to specify that we want to compute loss with MAC on the cross entropy, and rest of the things will be done by the system itself. Similarly, back propagations through time will not be directly visible to you unless you try to develop RNN from the scratch, because this library will take care of the whole stuff. So going forward for the next question, in stacked or deep RNN, can we use one hidden state with feedback, one without feedback, or we need to take all hidden states layer with feedback only? So see, if you see the encoder decoder part, then you can easily understand that I have one RNN which has the feedback, then I have a context vector, and then another RNN which has the feedback. So it's not mandatory that every layer will have feedback. I can have more complex structure as well. So the encoder decoder will have two separate RNN, and in between there is one context vector which is the normal stuff that does not have any kind of feedback. So explain vanishing gradients and exploding gradient in BPTT. I have already elaborated like the kind of stuff. Uh, the thing is, if we unfold the stuff in the vanilla RNN, I can have a very long path. If I have a very long path, then this W will get multiplied multiple times. Now, if so, in a very simple thing, let's say W is a single weight parameter instead of a matrix. Now, if that scalar value that is getting multiplied a number of times, if the value if that value is more than one, then my value will keep on accumulating. It will go into a very large value. If the value is less than 1, if I multiply multiple times, then the value will be close to 0. So that actually leads to the vanishing gradient and the exploding gradient. Can we compute loss or loss for lesser number of time step? Like how we will apply BPTT of time series data? So in that case, you have, so not in time series, so you have to decide how many steps you want to unfold. So that's a kind of a hyperparameter that you have to decide. So are you going to unfold for 5 times or are you going to unfold for 100 times? So that's a hyperparameter that you have to specify. Can you also please tell RNN training similar to a training spiking neural network? So I'm not very much familiar with spiking neural network, so I will not be able to answer that question. What is meant by feedback from output? Feedback from output basically means the output is governing the hidden state. So in the vanilla RNN, what we have talked about, that the hidden state has an feedback from itself, but whatever I am actually predicting, that information is getting fed back into the hidden state. So sometimes it can actually happen in some scenarios, like if my so whatever I am predicting as my output, that also comes as my hidden state. So it, depending on the problem, uh, uh, it can be there. Like, so this is not with respect to NLP, but if you think for a counter design, so you predict something and that counter value also gets fed back into the counter system to decide the what will be the next value. So so sometimes we can have that kind of scenario as well. In the last example, text question was how many horses are there. If there were another question, how many human beings are there, do we need to build one CNN and two RNN, that is each RNN for each questions? No. So you will have, uh, so what you can do, so you can treat this model in this manner. So you take the image, you take the first question, you produce the output. You take the image, you take the second question, you produce the output. So you don't have to create two RNNs. The kind of scenario, like let's say if uh, for every image, if you have two questions, then probably you can have two RNNs to process that stuff, but that's also not a very useful thing. You can have one channel for CNN and one channel for image, one channel for RNN. You just repeat for the next question. So that will be sufficient. Can we use RNN for large text summarization? Wouldn't the past information get diminished after sometimes if the sequence is too long? Yeah, it's the basic concern for the long dependency. So if you go for LSTM and GRU, it can perform well. But these days, most of the language processings are done through transformer, so not with the RNN kind of stuff. And transformer actually produce lot better results, and it produce better result because it scales well. That is the one important thing. But it has large number of parameters compared to your RNN. And then one questions, how video processing using 3D convolutions and using RNN will be different in terms of retaining the time information. So 3D convolutions actually stores that stuff. So typically when we do the convolution, we talked about a 2D convolutions that lose the timing information. 3D, if it's a 3D convolution, definitely it will have the time notions. So, but in that case, the computations can be more because you have to do a lot of computations. So in that case, in order to simplify the stuff, you do a 2D convolution, you extract the feature. So this extract the feature means it will be a reduced set of feature. Now you have the reduced feature over the time step, and then you take all those reduced feature over the time step, and you process that through the RNN and try to predict that stuff. So it's a kind of a trade-off. So it's not necessary that the CNN and RNN combinations will give the best results. Sometimes 3D convolutions can also give the best results. So you have to really see which one actually works well. In spiking neural network, we first keep adding the inputs, retain the state of neurons until a threshold is reached, and then we get output from the neuron, and simultaneously the state of the neuron is reset. The process is similar to RNN. In this, we use BPTT for training a spiking neural network using number of time steps similar to RNN. But here also problem of gradient skipping is observed. So I wanted to know how to overcome such issue, like how approach training such a uh, okay. So right now I just need to look into the stuff. I got some idea what you are trying to mean, but in order to answer your questions, I would it will be good if you can drop me an email. I will try to answer because I'll note down this question because I'm not familiar with spiking neural network. I really need to look into the actual stuff and then probably I'll be able to answer your question. So I have noted down your questions. Uh, Feel free to drop me an email, and so I will try to answer your question. In this, you will get the slide set, and the slide set you will get my homepage. From the homepage, you can also get. And okay, let me type my email ID here also: orijit@iitp.ac.in. Okay. So, sorry. Yeah. So, I think I I did not send to everyone. Just a second. Sorry. So it's orijit@iitp.ac.in. So let me know if you have any other questions or doubts.
Sir, I think that would be it.
Okay.
Thank you so much, sir, for such a detailed and insightful session. The practical perspectives were immensely valuable and are truly appreciated by all of us. Sir, I would also request you to kindly share the slides so the participants can refer to them if they encounter any problem during the practical session.
Okay. Sure. I will share that stuff.
Okay, sir. Sir, I will contact you later regarding that.
Okay.
Okay, thank you so much, sir, for joining us today.
Okay. Thank you. So
Participants, we will be back at 2:30 for the practical session of this. Thank you
so
very much.
bye.